All right, well, let's get started. Thank you all for turning out. Today we are lucky to have an atmospheric science departmental visitor, David Parsons, to speak to us. David is, he knew going into college already that he wanted to be a meteorologist. In fact, instead of going on a track scholarship to out of state, he went to his local university, Rutgers, because it had atmospheric science. And then went on to the University of Washington for a PhD, working with Peter Hobbs, and got a postdoctoral slot in Boulder, which rolled into a 25-year career at NCAR. These were great times there. And he's done so many kinds of observation from so many dimensions there, just impressive, as you'll see. After that, after 25 years, he took a stint at WMO in Geneva, just as a visitor or whatever. Is still employed at NCAR. And when he came back from that, he got roped into chair duties there at Oklahoma, and he's emerging from that, and maybe rejoining like more of a research-minded point of view. So it's great to hear his life journey and stage of time. I should say David was a huge influence on my career, because when I was after I had a postdoc fellowship, I was facing the employment market after a postdoc, the hard time, as you all know, the cliff. And it was right when Newt Gingrich had decided that what we would now call the first government shutdown was a good idea, and so everybody was sitting on their money, because who knew what was going to happen to publicly funded science. So David was my ghost PI, helping me write a proposal. I didn't have it. If you don't have a job at an institution, you can't write a proposal. But if you don't write a proposal, you can get a job. So anyway, he helped me thread that needle, and here I am today, still in the field. So many thanks for that. All right, he's going to tell us about nocturnal convection.
Okay, thanks, Brian. I usually tell the story the other way around, that it's an honor to have been working with Brian Mapes early in his career. So this is the title, and it's a bit of a thank you to Brian. Is Nocturnal Convection Gregarious, but also does the rain in the night stay mainly on the plains, and my sponsors are down below. When you're done with 20 years of management, you just get so excited about research. So this is some of the people that contributed to what I'll be talking about today, and some of it's very preliminary, some of it's been published just several years ago, and you can see from the list of topics that my topics are pretty broad, and unfortunately for you, I've tried to jam as many of them as I could into this 55, 60-minute, 50-minute slot, and I've decided to also sneak in some deep learning stuff, because that's so trendy. It's hard to give a talk without something with deep learning. So this first slide really talks about, part of it's supported by NSF, so the broader impact, using the European Centre slogan, weather matters, global NWP matters, and bus impact not only forecast skill, but also associated with the regime change, so that makes sub-seasonal and seasonal forecasts extremely difficult, but even just number-wise, it will degrade the sub-seasonal forecast. And most flash floods over the eastern two-thirds of the U.S. occur at night. There's sometimes other high-impact and severe events that occur associated with nocturnal convection, and these nocturnal storms really account for a big part of the precipitation for the corn and wheat belt for North America, and climate and weather models don't do very well on these nocturnal systems. And other regions of the world also experience these nocturnal convective systems in similar environments. So the talk's built around three questions, and the first one is really, why do we get forecast bust? So this is anomaly correlation coefficient from a slide from one of Mark Rodwell's talks. And typically you're up 80-90% depending on which model, and you get this tremendous fall off, forecast bust, dropout sometimes they're called, and then it can take several days for things to recover. So the first thing these nocturnal MCSs are actually associated with downstream forecast busts over Europe. So I'll start from the large scale and then work to the smaller scale, kind of backwards in case I run out of time. So the evidence for nocturnal or convective systems and bus goes back to Grazzini's work in 2002, saying convection over the Great Lakes tends to be associated with bus over Europe. Mark Rodwell linked this to trough over the Rockies, high Cape, and MCSs over North America. Sam Lillo and I and Mark followed up on this, and Mark said there's also ensemble uncertainty. So not only is the deterministic forecast bad, but the ensemble says, don't worry about it, it looks really good. But things are terrible. And then this next slide really just is from a paper by Sam Lillo and I, and it shows the pre-bus. This is 500 millibar heights and post-bus, just to reinforce the idea that what happens, this is from a cluster analysis, but what happens when there's a forecast bus, there's often a regime change across North America and the Arctic. So if you don't capture this, then the Arctic's even off in the forecast. So a lot of these efforts have been really looking at bus have been really associated with kind of looking at a large number of studies and maybe one case study. So I've looked at a period for study during the Plains Elevated Convection Campaign Pecan, and this is kind of the region where the busts occur. Southward directed, this is from Wallace, southward directed is midnight convection. So it's midnight, 6 a.m., noon, 6 p.m. So look at this, you're mostly afternoon convection. I don't know if that's really right, but and then the length of that determines the amplitude of the phasing. So you can see this region is a big nocturnal region that's linked into bus. And then the other reason for picking Pecan, there was a lot of instruments out there, but 7 busts occurred in the ERA interim forecast. They actually make a forecast based on ERA interim. Now they're probably making an ERA 5. And then there was 4 busts in the operational European Center model. So this is a really bad period for them. And so the bus cutoffs are usually just...
The time of year of this actual field campaign?
This field campaign, it was a...
Forecasts were bad.
Yes, yeah, abnormally high. So here's kind of the cutoffs, anomaly correlation coefficient below 0.4, RMSE 60 meters or more. And you can see there's these periods where maybe one day is like that, but we're interested in this period of very low anomaly correlation coefficient for 6-day forecasts over Europe. The ERA 5 winds, 250 millibar, 850. You can see there's this Arctic connection going on, but a very strong jet over North America. And then at 850, you have kind of what people would probably call a warm conveyor belt over the Atlantic that's taking place with a little bit of low circulation. So one of the things that we noticed is that convective systems, if they occur near the jet stream, they tend to occur where you have a Rossby wave dynamic. So there's a southerly flow, convection breaks out near the southerly flow, and then as the convection intensifies, the southerly flow intensifies. So it's as if the convection is getting locked onto the jet stream. And then if you go downstream, you can see you start getting some downstream northerlies. And if this whole thing persists 8 hours or more, then you wind up getting the northerlies increasing downstream. So you're getting this anticyclonic flow from the MCSs. It's a bit reminiscent of the ET type thing. And if it goes for 4 or 6 hours, and the atmosphere says so what, but if you're cranking a strong system for 8, 10, 12 hours, you get this Rossby wave response on the jet. And here's the surface obs. Kind of have a weak low pressure system and a low, but the European Center is trying to put the, this is an error in the 4-hour forecast in pressure, and here's the observed sea level pressure. So the low is in here, but the European Center is trying to put it up there. This low is all associated with convection. So there's even some coupling with the surface that the European Center model isn't getting right. And then this was a bit of a surprise that we had this period of strong westerlies that I showed, but you can see there's hints of jet streaks that happen with this southerly, northerly downstream intensification. But if you look over here, this is kind of the typical Rossby wave group velocity moving downstream. Here's the northerly, southerly flow with the troughs and ridges. But during this bus period, instead of having this slow phase speed, you essentially have this very rapid phase speed, just jetting along. The convection gets coupled with the jet stream, starts triggering Rossby wave downstream, and the whole thing's really moving fast. And just to bring that home, kind of the wave number and frequency plot power distribution for Rossby waves. This is a normal June. And then for this period, wow, you're up between, there's a lot of energy between 10 and 15 for the Rossby wave numbers. And people actually filter this stuff out. So that's another story that I won't really go into. But you can see that it's definitely something unusual happening. Sam Lillo's developed an error amplitude and that error in the wave activity flux, and you can see the errors begin in the ridge, as Sue Gray and others have found. Tends to propagate downstream as a Rossby wave packet, and then things really amplify like mad over the North Atlantic. And interestingly enough, and maybe not surprising when you have these long-lived convective systems that are coupled to the large scale and moving rapidly, that if you look at most of the bus studies or go back, you'll find that there's just a tremendous number of severe weather reports associated with these convective systems that tend to be poorly forecast and linked onto the jet. This is the average stream function error for spring, April, May, June for 8 years from Sam Lillo's work. You could see this is this, and over the continent of China, this is the biggest errors on the planet occur there. But surprisingly, this is a plot of that error amplitude, bust minus good. So there's nothing really special. We're always getting the Midwest convection wrong, but it's no difference between bust and good days. But one of the things that happen as you move forward, now this is 72 hours, you can see this is bust, so there's a lot of error. The blue is where the forecasts are good. You could see that what's happening is you have this Rossby wave break area, poleward wave activity flux that's occurring, and that area is where the error amplitude really takes off. And you can see it's marching across the Atlantic. I mean, marching across the Arctic, marching across Europe. So you have these convective systems, but really things start going wrong. But where things really explode is with the jet over the North Atlantic. And based on this, Sam has put together a conceptual model for his dissertation of Rossby waves on the waveguide, and then they tend to be triggered by tropopause polar vortices coming out of the Arctic, convection near the waveguide, tropical cyclones, amplify, move downstream, and then wave breaking in the Arctic. So,
Dave?
Yes.
It seems like some of the plots you're showing physical fields, and you're talking about propagating Rossby waves.
Yes.
Some of the plots you're showing error fields.
Yep.
Is that the same thing?
Often, yes, but not always.
You know what I'm
Because
saying? Like, should
yeah.
we basically consider, if I see an error between a model and analysis,
Yep.
should that error like, should it propagate like a wave and have,
Yes.
have a dispersion
Yep.
relation and a
So-
phase, you know?
So if the wave packet didn't exist before, then it's the same. And some of these it didn't exist before, but that's not always the case. So I think often what's happening is you're triggering a Rossby wave that's not in the real model, and it's going downstream, amplifying and breaking, but that's not always true.
Okay. All right.
I hope that helps.
No, that does
I
help.
wonder about the same thing. So ongoing work, we're actually trying to work with radar data and the European Center model. They've done reruns and hourly saves. Peter Bechtel called him the convective whisperer. We're trying to figure out what's really wrong with the convective parameterization. It's maybe a bit too early for that, but we have some ideas. And then I had to sneak this stuff in that we're actually trying to look at deep learning to predict why forecast busts will occur, but then also couple this with the dynamics. So we're looking at 1989 to 2015 bust and non-bust events. We train the deep learning on 1,200 bust events, 2,400 non-bust, and then we withhold some sample and test it. And busts are divided by season to look at the errors following Lillo and Parsons. And we have multiple heights, and the cool thing about this is actually if you take out a height, you can degrade the skill. So it's actually, you need 250 and 300, not just one or the other, UV and geostrophic wind. This is the convolution neural network architecture we're using, and I have to admit I'm very embarrassed to say that I have no idea what this means. It's stuff that Chris gets off of GitHub and tells me about it and gives me a paper about people that use it. And sometimes it's actually in the medical field, sometimes it's atmospheric science. And on a good case, we don't think we're overtraining. We get 75 to 88% of bust cases identified just looking at the initial conditions and trying to predict what's happening downstream. And out of the incorrectly classified, it's almost an even split on false positives and missing the bus. And then this is really preliminary stuff, and ignore the wind vectors, but these are sensitivity hotspots. So red is where it really matters. So at 200 millibars, this Rodwell trough thing does show up. Blue where the computer doesn't really care, the algorithm doesn't really care. But this is one thing that we have to see is this area up in the Arctic where the Rossby waves break also tends to show up. So this is kind of preliminary, but we've just started to try to interpret the deep learning in terms of the dynamics. And some of it makes sense. The winter I didn't show here. Busts over the winter really care about the jet stream over the North Atlantic. But the fall, you wind up with this strange area. This is like the TPV well and sometimes Rossby wave breaking up there. So this is really preliminary. Don't believe it too much, but we're starting to move down that area. So just in summary, it's well-known forecast errors in the mid-latitude propagate like Rossby wave packets. However, the high wave number Rossby waves have received far less attention. There was a paper by Joe Trivia and Baumhafner way back 2004 that said in climate models, rapid error growth occurs with high wave number disturbances. So this is just several cases. We've published this, you can see down below in atmosphere. And it appears that if you have strong, long-lived MCSs near the jet stream, you can trigger a Rossby wave response. It doesn't have to be persistent convection for days, like in the Dave Stensrud studies, which are good studies. And isolated convection, supercells, short-lived MCSs across Alabama and Miami, unless they're near the jet stream, it doesn't really matter, except for the people in those locations. They don't produce a wave response. And this idea that the MCSs near the jet stream matter, long-lived MCSs, it's actually, Lorenz had a kind of a caution in his paper, and he was saying that he basically said that, okay, if you care about convection, convection occurs near fronts occur near upper level troughs. So if you have idealized studies, you can actually maybe not, should have some caution because it's not the same as really getting looking at something where fronts, convection, and trough are all together. So this actually fits Lorenz's caution a bit. So it matters where and how long the butterfly flaps, at least in mid-latitudes. The coupling between the MCSs, fronts, and the jet stream has some similarity to diabatic Rossby waves, Maxi Betcher and Heine Wernley's paper and others. And the inability to capture long-lived MCSs coupled to the jet stream, I think this is maybe a little bit different than basic predictability experience. You have convection, those great papers by the late Fuqing Zhang. You have in others, you have convection, you put out a Rossby wave, there's a geostrophic adjustment, and then it goes to the large scale. This basically says the convective errors can be coupled to the large scale errors for 8, 10, 12 hours. So you're not getting the convection right, it's coupled to the large scale for many, many hours. So it's not just some convection happening, it affects the large scale. There's a scale interaction that's going on. So that's one thing. And the convective errors over North America are only the seeds, but really matter. And there's more behind this, but what really matters is conditions over the North Atlantic. So, does the rain in the night stay mainly on the plains? And I say no, sometimes MCSs race towards Europe on a high wave number Rossby wave train. So that's kind of the first part of my talk. So maybe we're trying to make a joke and answer the next part of it. So the next part I'll get into nocturnal convection. Why does this maximum occur? It's been long known, Kinser 1916, that Great Plains has a nocturnal max, but we're still not yet a consensus in the scientific community as to why this occurs. So let's look at this source region for convection and forecast errors over North America. And one thing about this, people know probably there's a southerly low-level jet that's been talked about for many years. It's tend to be linked with deep convection. People know about the Blackadar mechanism for the atmospheric scientists in the room. Basically, you have a, say, southerly flow in the boundary layer, top of the boundary layer. The turbulence shuts off. The wind goes through an inertial oscillation, and this has been argued as a mechanism for the low-level jet. And then also the fact you have terrain looked at with a constant buoyancy, that the fact you have terrain with a constant buoyancy, you wind up having a baroclinic type effect, and that was the Holton mechanism. So you have this low-level jet that's usually argued to be a Blackadar type thing. So what we did, we looked at 5 sounding sites over the central U.S., and the ARM program was nice enough to launch sondes at 3-hour intervals for almost a month. And this sits in the area of nocturnal convection. So one thing to look at, there's been recent analytical studies that suggest there's both a jet in the U component and in the V component. Sun rises here, sun sets somewhere in here. So you build up this southerly at night, and you do have this also a U-type wind. So this is kind of quite a bit different than maybe just people thought of the pure Blackadar mechanism. So when you look at the sounding data, V is on the bottom, U is on the top. You do get a U and a V max over the planes. So this is sort of different than the basic low-level jet theory. These analytical models and theoretical models by my friends, they're right. And but the U max, you can see it varies a lot with time, and the max tends to descend, and descend much more than the V max does during the night. But it's really impacted by the background flow, vertical shear, etc. So the U max is quite a bit tricky. One thing we looked at was the error 5 theta V at the surface, and we noticed after a front goes by, this is the southerly component of the jet and the westerly, and the surface theta V. What happens is that the buoyancy gradient builds up, and the easterly and westerly wind components associated with the jet build up. So a lot of times this is something turbulence people work on. They're looking, does the turbulence nature change? And this suggests maybe there's a synoptic influence, or the fact the slope's so large, you have buoyancy gradients on it, really matters. And then what we did was just calculate the geostrophic wind, the maximum geostrophic wind down low in the dash, and then here's the real wind. And you could see that this is after 2 frontal passages, that the jet's really building up because the geostrophic wind is building up, and the geostrophic wind is building up in a large part because the buoyancy on the slope is building up. So the idea, there's still an ageostrophic enhancement on that people could argue is the Blackadar mechanism, but basically, you know, this large-scale geostrophic flow that's set up with southerly flow, but then also the fact you have heating on the slope, and the slope has vegetation and soil moisture gradients, etc. So this is maybe one difference, that this synoptic forcing really matters. And another one, too, that we noticed that early in those periods, we tend to have a really strong nocturnal boundary layer, stable nocturnal boundary layer. And as you get later in the period, what happens is you tend to almost have a well-mixed boundary layer at night, topped by a stable layer. And one thing we've been looking at, we haven't separated out the cloud field from clear air, but this is the long wave downward directed radiation during the first frontal period, during the second, and then this is that frontal passage. So what happens is you're building up the jet, at the same time you're not cooling the surface. So or cooling the surface less. So you're mixing like mad. So the nature of the nocturnal boundary layer, you know, really cares that the jet's getting stronger and the jet's pushing up higher and higher water vapor air, and you're getting low clouds. And just to save time, I don't think I put that figure in. But then this is a composite over the period where we had those 5 sounding sites, just looking at the time where there was a southerly low-level jet, and you could see that we do have both a U max and a V max, the U max above, so the people tend to be right in terms of their analytical model. And this was a bit of a surprise. The best conditions for convection are during the day, but we're getting a nighttime max. There is this secondary max of high cape with the jet and a reduced sin with this westerly layer aloft, but it's a secondary type max. that's kind of a composite, and I think Mike Wallace used to say no such thing as composite weather, so you have to look and see what's there. So what's happening locally, this is actually a paper from Ben Blake and I, a master's student who's now at NCEP, and this is just a squall line with Wharf. And one thing that he noted in the observations for that paper is that the instability, so the high cape air with the jet, is really pretty narrow, and it's associated with high moisture. This is at 2 different times. So, okay, so on the mean, the daytime's better, but wow, locally at night within the jet, this is pretty difficult. And you could see these kinds of 50 kilometers across, something like that would be difficult to get right in a coarse grid model. And then this I'll just maybe talk about pretty briefly. So this is a Cape Sin plot. This is when the first convective system started. This is at 1 kilometer. This is at the surface. And things were pretty good. Cape over 1,000, a fair bit of Sin, 200 and 200. But as the night progressed, things just became less and less stable at the surface, a little less stable aloft. But this convection reinvigorated when it hit that moist air, and you can see that the Cape Sin goes from over 200 and about 500 for the Cape, all the way down into this space over 2,000 and Cape under 1,000. So locally you really can still get the most unstable air masses at night. As the boundary layer stabilizes. So kind of a summary thus far, there is a U and a Vmax with the jet. Umax is located above. The intensity of both the U and V seem to be linked to the synoptic framework and intensifying east-west buoyancy gradient on the slope, so that the large southerly wind at night the large jet at night is really not due to the Blackadar mechanism alone. The Blackadar mechanism is a bit of an enhancement on this strong southerly flow. It just creates an geostrophic enhancement. And Parrish noted this, the importance of the background geostrophic wind in a case study that he did. And many analytical studies have constant buoyancy on the slope, but we have a buoyancy gradient, so this is essentially an expansion of the Holton-Barraclinic mechanism, which has actually often been overlooked in favor of the Blackadar inertial oscillation thing. And then an increasing southerly jet, you get more water vapor and weaker nocturnal stable boundary layers, stronger winds, less surface cooling through radiation. And generally, us mesoscale folks and the turbulence people looking at the jet tend to ignore radiation, but it turns out it's important. So now we're trying to look at clear air versus cloudy conditions. So, oh good, I'm talking fast, maybe too fast. But the third part is really these continental nocturnal mesoscale convective systems. Do they have a different structure and maintenance mechanism than conventional MCSs? We've been proposing this in recent studies, and I have a schematic from the House 2004 review paper, and this schematic, talks. This doesn't say all systems are like this, but you tend to have a gust front at the leading edge, and it's triggering convection and a big stratiform flow, descending rear inflow, ascending rear front to rear flow. This is the one that the jet stream likes. And with nocturnal stuff, you tend to have this deep impact both ways, at least we think. So, if you're having a boundary layer that's stable or sometimes well mixed with a strong stable cap, how well do these schematics hold? So nocturnal convection needs to thrive when there's a stable boundary layer and potentially unstable air aloft, like that Blake paper up at 1 kilometer. Things are just better than the daytime. They're ready to convect. And so the maintenance mechanism might be quite different from conventional thinking, unless you have super strong cold pulls. And I think that the evidence is there that these nocturnal systems often look quite a bit different, starting with Rob Flavel's work quite a while ago and others, that they noticed that convection at night tends to not be often, not always, but not quite like a squall line with continuous propagation, but discrete propagation. Cells popping up, things kind of vercellular, they move along sometimes rapidly. And this is from a paper by Steve Koch. I tried to pick out the prettiest plots of showing this. So this is when there was a gust front and you have this MCS type system, but this fine line's moving out ahead, and now you're getting this wave structure I'll talk more about, and you're going more to a cellular thing and things popping up here and there. So they look quite a bit different than the typical MCSs. So our ongoing research theme, one of the themes we've been looking at is that the convection in this nighttime environment will generate bores and gravity waves, and these provide strong lifting that help initiate and maintain deep convection. It's based on a number of case studies, idealized simulations by Matt Parker and Mike French and Parker, and also we're influenced by the gregarious convection that Brian talked about in subsequent research, that the waves and other things besides gust fronts are important. Basically, the thinking here is the daytime you have an unstable boundary layer, gust fronts matter, but when your unstable air is up at, say, 750 air with a lot of sin to above that with less sin, how are you going to keep convection going? How are you going to keep a gust front even going when the boundary layer is so stable? So I'll start with some work by Kevin Hodge. Left and went out to, after his doctorate, to the University of Washington, and he classified, he's a kind of a person that loves theory, but he got the idea to classify all these radar fine lines from a 6-week field project, and then use surface data to try to tell what's going on, and then compare this to theory. And this paper was out a few years ago. And for those that maybe don't know what a radar fine line is, here's some convection, and these fine lines pop up because of refractivity gradients, and over the continent also insects are converged and lifted into these areas. So he was looking at tracking all these fine lines, whether they came from convection, what their lifetime was. And then in Oklahoma we have this mesonet that's pretty dense, so we could look at the characteristics as these fine lines went by. So did the fine line have a temperature drop and a big gust of wind? In that case we'll call it a gust front, a cold pool. Did it just have a huge pressure jump, a couple millibars, and no cooling at the surface, or maybe some warming? Well, it's probably a bore. There's other things going on, fronts and heat bursts and other things. But what he did was he looked at 58 cases where he could determine what was going on, and you could see that almost all of these, 44 of them, turned out to be bores. Only 6 remained density currents, and some of those were near the edge of the domain. If we had a bigger domain, they might be bores too. So these pressure jumps without temperature cooling happen a lot at night, and basically density currents trigger bores, and then often the density current seems to go away a bit, which is kind of interesting, and something else we're working on. There's theory behind that. I just had to show some equations, but let's not talk about it much. But you have these vertical variation of the score parameter works with trap waves, and you have these other things to determine the speed and the nature of the disturbance. And this goes back to Rotman and Simpson's work of flow over a mountain. So for let's say for a density current or a mountain, a hill, a bump, you have air approaching it, and eventually that air can become stable, or the stable layer is so deep that you can't get it up and over the density current. So essentially you get partial blocking, hydraulic jump if you like, or a bore forms and races away from the density current. So that's, you can also get complete blocking, you get supercritical flow up and over, subcritical flow, etc. And Steve Crook, Andrew Crook, and others did simulations with a compressible atmosphere and density currents. And Mitch Moncrief also, I think, and made the leap from hydraulic theory to mountains and cold pools and atmospheric flow. So here's that same kind of diagram, and you can see the partially blocked lies in here. So what Kevin did next is he would take a sounding, grab a sounding, go over here, randomly grab a cold pool, the orientation of that cold pool, and see where it fell on that diagram, and did it as a function of time. So what he found that as the night progressed, on average, you tended to have the cold pool interaction really have a big centroid in the partially blocked. So this goes with the nature of the radar fine line. So as convection gets going at night, it's going to tend to produce bores. which is quite different than daytime convection. But also the other interesting thing is, it's a good lift mechanism because daytime you have surface cooling, at night the instability is aloft, and so bores or even n=2 mode gravity waves have lifting above the surface. It becomes a more favorable time for them. And I'll just show with some vertically pointing profiler data, vertical velocities here, and the signal to noise. You can see what these different bores look like even in a 3-day period. Here's sort of one jump. Maybe it's more like an internal gravity wave. I don't know, because it's not much happening here, but you get this jump in this area, but it doesn't really go back down. Sometimes you get these strange waves with different waves and different speeds in different layers. There was a paper with Sushi Zhang and I that came out recently that suggests even under the right conditions, if you have a critical layer, you can get bores and stable layers aloft, but you can also get n=2 modes. And then sometimes you get these cool undulate bore wave trains. Here's vertical motion. You can see how nice this pops up, and this is right near the top of the trapping layer, and you're getting this, but you're also getting a different response aloft. And so what we did was we took the pre-bore height of a scattering layer and the post-bore height, and we looked at the displacement of these layers, and the displacements are sometimes quite large, well over 1 kilometer. In the mean, they're 700-800 meters. So the study that I was involved with, and then with the IHOP, and then Fearless et al., Dave Turner did it with the Pecan data, and on average you're getting a net upward displacement. That initial lift could be higher, but the net upward displacement of about 800 meters. And it's up in that area where you want lifting, where the instability is. And this lifting can remain in place for many hours in the wake of the bores, and it can cover areas of 10 to the 4th kilometers squared. So that's a little bit like the stuff Brian likes. These things rush out. Other things are happening aloft too that we have less data on, but they last for many hours and cover a large area. And the bore structure varies and likely includes other wave responses. So late afternoon, as you get to the night, you can have this partially blocked regime, air still going up and over the cold pool. The curvature of the wind, the fact that you have a U and a V means that trapping varies in 3D. Deeper waves are allowed on the eastward side, and then trap shallow waves looking into the southerly max. And then sometimes you get bore-induced convection, and this, it varies with the conditions. So you get behind the bore, you can have many of these little humps. You start getting cells breaking out, and you wind up having discrete propagation. So in the end, fixing the bus is a pretty big challenge, I think. You have a nocturnal environment that you have to accurately represent surface temperatures over a large region. The daytime boundary layer depths have to be right. The vertical profiles of the advection of heat and water vapor, turbulent mixing, differential advection, and radiative transfers. You have to have all of these to get this right. Analytical models in that first composite I show you likely oversimplify the jet because there's local instability. And so simulating nocturnal convection with a convective resolving model depends on getting the cold pool right, which is already a challenge, and then the wind's instability within and above the stable boundary layer. Stable boundary layer is a challenge, and then getting this interaction right. And bores are a non-hydrostatic response, so convective parameterization is difficult, and coarse grid spacing 3 to 5 kilometers doesn't do well on bores. You can see paper Roy Rasmussen and people from NCAR wrote, and 4 kilometers, they do great on convective systems, but not at night. Well, the board literature says 4 kilometers wouldn't help you at night. They're non-hydrostatic and local. So, does the rain in the night stay mainly on the plains? No, sometimes it hops on a wave train and is nocturnal convection gregarious, and I said yes, with bores, gravity waves, and Rossby waves, their impacts spread. So thanks to ONR, thanks to NSF, I forgot the recent grant number, and that's all I got. So thank you very much for your time. I couldn't figure out a way to work the ENSO stuff in, I'm sorry. Questions?
Go back
Sure.
to the bore diagram you just showed.
Was the Kevin one, or?
It's just like one of the last cartoons. Yeah, before that. Okay, so you're saying the nighttime situation, Does the bore lifting then propagate away, or is you talking bore lifting creating convection right there?
So actually, so this kind of thing, as the bore goes away, it reduces the stability and things can keep going. So that happens sometimes. But if this amplitude's large enough, then it can actually...
Does the bore propagate to the right in this figure? Or
Usually. So it depends on a parameter called mu. And typically with the mu, this is moving away. But not always. Sometimes it can remain locked on.
The bore's going like upstream against...
Upstream, yep.
Okay, so the bore's propagating
Yep.
upstream against the flow, possibly creating convection down
Yep.
upstream somewhere.
Yeah, and as it's longer lived, then you tend to go, not always, but you tend to go to unnewer type bores. And so, convection breaks out somewhere behind on, one of those peaks. But yeah, this usually moves away. It's really interesting when it doesn't move away. Depends on the wind profile and the bore amplitude. When it doesn't move away, then what happens is these circulations tend to get locked on, and you can get a little runaway cold pool, where this cold pool is it's like a density current head, and the bore just march off together pretty rapidly. And Sushi Zhang, who's back in Nanjing, or outside of Nanjing, got his doctorate at Nanjing, but he spent 1.5 years with me, and we're actually submitted a case that looks like that, where these things are locked on and you get a density current head that runs away.
Could that also make new convection, or that's a different?
Yeah, it did. It did, but then it moved eventually into an environment that was not so unstable, and it died.
But in the daytime, this was about nighttime convection.
Yeah.
In the daytime, because you wouldn't have your stable boundary layer.
Yeah, everything tends to go just up and over.
I see. I think.
Yeah. Peter?
Yeah, the fine lines that you saw, those could all be traced back to some convective event.
Yep.
So are these similar to what we see in the Florida radar loops, where you see the little
Probably. Yeah, probably.
stuff, and sometimes when they merge, you see something?
Yep.
Or is
Yep.
that more the density current?
Yeah, so their fine lines are often with density currents, and daytime convection, they tend to be density currents, and then, at night, they'll transition into bores and other things. And I think Kevin Nutt up in Alabama sees bores sometimes and has written about them in Alabama. I don't know if they're occurring here, if you got a stable enough boundary layer or not, but it's pretty common. Sometimes there's people will publish a satellite picture over the Gulf of Mexico with a bore, so they do happen.
What would an aircraft be able to see?
So there are papers, Bart Gertz and others have written where they've actually have aircraft passes through bores, and so they are able to do multiple levels and watch that. So, Ricky,
How did you deal with forecasts in the field for pecan? Were they still useful to you, and did you learn anything from those that were useful for later analyses?
so it's interesting because the forecast team was really variable, and Kevin Haji was involved quite a bit. And after looking at hundreds of fine lines and the large scale, some of the forecasts did a very good job, and others didn't do such a good job. But we did a dry run the year before, and that helped a lot. So I think in general the forecasts were surprisingly good some nights, and sometimes there was one case that Kevin was the lead on, and there was actually a convection moving along, and he said, well, it's going to move along, and then it's probably going to turn to the right with the bore. So they set up to the south of the path where convection was supposed to occur, and we actually nailed it. Other cases we didn't do so well. And one thing that happened in Pecan, the severe weather people in the program were always wanting to chase the biggest storm up by the jet. So I think there's a lot of studies that are of diabatic Rossby waves, and squall lines that were associated with things where the large scale also matters. So it was a bit all over the place, but forecast did better than I thought. And then there was also Dave Imey, who was a retired SPC forecaster, was there, and he spent a lot of time with us before the project. So he was pretty excited about this stuff, and so I think it kind of came together. Sometimes, and other times it didn't. And And there was also a tendency to move to where the strongest convection was, and sometimes that was up near the jet and where there's fronts, and because that was the most certain, and they weren't so sure about these other things that would happen further south in the domain. So that was kind of a little bit of friction in the experiment. Oh, head scratch. Okay. Yep.
So you showed that towards the beginning of the presentation, the error propagation, and so you can kind of see that busts and MCSs can kind of lead to downstream Rossby errors. But like, is there another signature or like a footprint that you can see besides those error diagrams? Because I guess I kind of had trouble with that reason as well.
Yeah, I didn't really define what the phase-independent error amplitude is, so everybody should have trouble with that. One of the things that we've been doing is looking at the error 5 reanalysis V-winds and then comparing that to the European center. And so that's one way to, and it's nice because it's a physical interpretation of the error. And one thing we're finding out is that that difference between what we think is the reality and the radar data in error 5 versus what's in the forecast, it really varies by height. It's as if, I'm speculating, almost as if they're getting the divergence associated with the convection in too shallow of a layer or something like this. But so we have been spending a lot of time looking at the the V-wind, and trying to figure out from that what's going on, but we're not there yet. So, and believe it or not, there's one thing that's nice when you have 50 undergraduates. Some of them are just like superstars, and so the undergraduate that's been working on this project is over at University of Reading on an exchange semester, so it's kind of stopped, and I think I'm going to go over there, and that we're getting together with Peter and company to try to figure that out. No, it's a good point, and we have been trying to look at the V, but it's actually have some V plots that were going to be in the paper, but the people said, reviewers said, it's getting too long, take it out and do another paper, so I didn't put them into the talk, but that's a good question. Yes?
So on this topic of the errors, you showed the power spectrum over that 1 week-long period.
Yes.
That was a bust, and you showed that the high frequency, high wave number,
Yes.
wave activity was occurring in the analysis. Have you also looked at the power spectrum from the forecasts to see if it's getting that wave activity?
No, that's a
correct?
brilliant suggestion. No, we
Because I would
haven't.
tell you if it's an amplitude error or a phase error.
No, that's a brilliant suggestion. Just looking at the fields, it doesn't seem they have that rapid phase stretching, but you're right, we haven't shown that. That'd be a good thing to look at. So we suspect that those waves aren't in the forecast, but showing it that way would be nice. The thing about the European Center is, you don't write a grant, they just have people working on this stuff. Mark, could you please do that plot? That's a really good suggestion. Other questions?
All right. Well, thanks again for coming, and to the speaker.
Okay, thank you.